All right, so this is our procedure. How we're going to try to construct the large models is we have the existing procedure that if you have the list of reactions, we can make the predictions. And everyone says we should do sensitivity analysis on the predictions in order to figure out which parameters we have to improve. We're going to improve them by doing high accuracy quantum calculations on the sensitive parameters. And then we're going to store them as numbers we know now, because we did that calculation. And the new thing that we're going to try to do is get the computer to build the model for us. So from this chemistry knowledge, we're going to try to somehow write down rules that the computer is going to use in order to know what can react with what and what rates they have. And then this program, the reaction mechanism generator, is going to automatically write this long list for us, the improved version of it. And then we might be able to go through this loop a few times and maybe make a good model. That's the idea. And instead of having a human sitting here and writing new reactions, we're going to have the computer write the reactions for us. All right, so what does this do? It makes models that consist of elementary reactions. It estimates the reaction kinetics and the thermochemistry, and it's open source software. And you can download it yourself here. And there's a pretty good documentation about it in this journal paper, Computer Physics Communications 2016. This paper only has a few authors listed on it, but actually a ton of people have contributed to this software. And you can read more on the website to get a more comprehensive list of the contributors. It's quite a complicated software package because basically it's trying to replace Charlie Westbrook or something, as Manny Sarathi is now inside a computer in your desk. Okay, so how does this work? So you're going to have to provide the initial composition of your mixture and the conditions like the temperature and the pressure. And RMG has libraries of kinetic and thermochemical parameters that are known well. And you can select which of those libraries you want to use. So you can make your own judgment of which numbers you believe. Because for a lot of the small molecules, actually there's disagreements about exactly what the numbers are. So this is what those entries look like. It has, here's OH reacting with H2 to make H plus water. And these are the parameters that RMG would use at the library. A was 2 times 10 to the 8th, and EA is 34, 37 calories per mole, and whatever. Okay, and so we have a lot of libraries like this, and you can select which of those library values you want to use. If you don't want to use the libraries, it's going to do estimates of the numbers. And then you have to specify your error tolerance number, which is going to translate into the termination criteria. So we need, as was said, we need to have a criteria for when we're done. RMG has its own way of formulating that criterion. It has a parameter in it, which is your tolerance, and you have to give it a tolerance number. If you make the tolerance number smaller, you get a bigger model because it won't get done. Right? It'll keep on growing. But eventually it'll get done, whatever tolerance you give it. You also have to specify how long you want to run the chemistry. So the chemistry starts, it's going to run for some finite amount of time. You have to tell the time. Or else sometimes people don't want to run a finite time. Instead, you want to run until a certain amount of your fuel got converted, for example. So you can specify how much of the fuel you want to convert. And then RMG is going to spit out a kinetic model that looks just like a ChemKin file. Okay, and you can run that in ChemKin or Kinterra or other software. All right, so it uses the rate-based algorithm to select which species to include. So this is how that works. You have the model currently. The computer enumerates a whole bunch of reactions that these species can do that make species that are outside the model, on the edge of the model, the first generation products. Then the computer estimates the rate coefficients for all those reactions. And then based on ChemKin solution of this model, at each time point, it has an estimate of the concentrations of the species. It uses those to actually convert the rate coefficients to the actual rates of formation of each of these edge species. So it says, like, if you allowed this species into the model, how fast would it be formed? So currently it's not in the model, but it's computing like the sort of the flux that's pressing against the boundary to get out, that you're not allowing out because you're not allowing that reaction to be there. But if you did allow it, how fast would the rate be? And if that rate number is big, then you say, wow, this must be an important species. So it assesses these guys, and suppose it finds out that propene is formed with a big rate, but HCO is formed with a small rate at your conditions, then it would say, oh man, this is really important. We better put propene in the model. So what it does is like an amoeba, the model boundary grows to eat up propene and put propene inside. So there's propene inside the model. This reaction's now inside the model. And then it will compute immediately all the reactions of propene with all these other guys to have now a comprehensive model for all the old species, all the old reactions, and plus propene reacting with every one of them, and propene reacting unimolecularly to make products that are already in the model. And then, by the way, at that same time, it will enumerate additional new side reactions. So for example, if you have propene, you could abstract an H from it to make allo radical. That additional reaction would be just enumerated as a list of possible edge reactions. Like your edge of your model changed because you moved a model from the edge to the core, you moved from the edge into the model. Then the new model's edge is bigger because things that were children of propene are now on the edge, now first generation products. Okay, so this is the algorithm, and again, you can go and download the software yourself to do it. And typically, with the tolerances that we usually use, we often end up models with a couple hundred species and a couple thousand reactions. You could tighten the tolerances and you can make them bigger. You can loosen the tolerances and make them smaller. Currently, my students, with the patience they have for how long they're willing to wait from the run, usually stop when it's something like a few hundred species, a few thousand reactions. If we could make it run faster, maybe they would make it bigger. All right, so this is the overall procedure. So we said this has to be iterative. So the main RMG algorithm is to generate all the possible reactions and intermediates using these reaction family templates. So RMG knows about types of reactions, and that's how it figures out that, for example, that propene could go to make allo radical. It knows that because it knows about that H abstraction is a possible family. It also knows that bond scission, the CH bond breaking, is also possible. So those would both give allo radical from propene. And there might be some other reactions that could do it too. And so it knows a bunch of reaction types, and it tries to systematically apply those templates of all the different possible things that can happen to every species and write down possible reactants. That set of templates is not perfect. So there's a lot of reactions in the world, and as time goes on, we learn about more of them, and we teach RMG as we learn about new types of reactions. But in combustion chemistry, there's maybe like 6 reaction types which like dominate almost all the reactions that you'll see in chemical kinetic models, and actually the real reactions that are happening are really of 6 types. You have like bond breaking, beta scission, additions, H abstractions, and you're pretty much done. Like that's the reactions that happen. And so if you just include those types of reactions, you're okay. But in the real world, there's also Diels-Alder reactions, there's Ene reactions, there's all kinds of strange reactions with names. Those of you who ever took organic chemistry, you learn about these funny names, the reactions. There's a lot of other reactions, and some of those we put into RMG, and some that RMG doesn't know about yet. If it doesn't know about it, it just means it will be omitted from the list, so those species would not appear on the edge being formed by that reaction, and so we'd really be underestimating the rate of formation of those species if we left those reactions out. So it generates all the reactions using the templates it's got. Then it estimates the kinetics and thermochemical parameters using group additivity for all the new reactions and species. And then it solves the differential equation for the revised model to get new estimates of all the concentrations, which it can use then to estimate the fluxes across the boundary from the model to the edge. And that's going to be the number that's used as the criterion for which species is most important to add next. And then chooses the important intermediates, generally the important additional species, based on which ones have the highest flux. Then, after you've done this and you have a model and you think is okay, then you say, I think my model structure is okay, let's stop for a minute, and now let's do sensitivity analysis on this model. And I know that a lot of my parameters are not good because I used group additivity to estimate the numbers. So now I want to figure out which of the numbers I want to refine. So I do sensitivity analysis. I find out I'm sensitive to 10 or 15 of the parameters. 5 of them are already great because somebody measured H plus O2 to 10%, so I don't need to refine that one. But 12 of them are terrible because I'm just using some stupid functional group analogy that might not be good. So I'll go do a quantum calculation for those 12, and I'll then improve those parameters. And then I'll rerun the sensitivity analysis, and I'll find out that with the changed numbers, things changed around. And now there's 3 other ones I have to compute, and I do those 2. And now I run it again, and now I find out that all the numbers I'm sensitive to are numbers I actually have good numbers for. So I think it's pretty good. So now I might want to go back to RMG and say, well, rerun it now because I have different numbers. Maybe you'll find some different species that are important to put in. And you keep on going back and forth between this refining the numbers in your model with a fixed structure and changing the structure by letting RMG add more species in. And you keep repeating this whole thing around and around and around a lot of times, and at some point you get tired and say, okay, I'm done. Okay. And then you're ready to try to compare your predictions of that model to experiment. You have to represent the molecules, the species inside RMG. We keep changing this because this is actually really tricky. Molecules are not so easy to represent as data objects in RMG inside a computer. So currently this is what we have, is we have a list of the atoms. We have a list of whether or not they have radical sites on them, if they have extra lone pairs on them, if they have charged, and then the list of the bonds they have to each other atom, and what type of bonds, if it's a single bond or double bond or something like that. So that's our current representation. This is intrinsically a two-dimensional representation. So methyl is not represented as a three-dimensional object. It's represented like this. It's really what's connected to what. It doesn't say how long the bond length is. It doesn't say anything about the geometrical parameters, the vibrational frequencies, or anything like that. And for small molecules, it turns out this is fine. For bigger molecules like proteins, this doesn't work at all. Proteins, the three-dimensional structure of the protein is like critical to the way it works. And if you try to represent this way, you'd have no chance. So at some point, when I have a lot of budget and a lot of hardworking students, maybe I'll try to change RMG over and have it all have three-dimensional representations of everything, which would be higher fidelity to be more like the real molecules. So far, we haven't quite got to that yet. These are the reaction templates for the reaction families. And we have reaction templates, which is the type of reaction that happens. And that'll tell you which bonds to make and break. So we have like H abstractions, internal H abstractions, additions to multiple bonds, recombinations, some migrations, some disproportionations. So we have some set of a bunch of reactions. So far we have about 45 different reaction templates of these types. There are different patterns of which bonds make and break during a chemical reaction. And they each have a recipe, which says, just basically, it says what reactions make and break. So it says if you want to do an H abstraction, you have to break a bond that includes an H. You have to form a bond that is the radical grabbing the H. And then you change where the radical was. So the radical was on atom Y, and now it's on atom X. Okay, so that's the recipe for that family. And we have similar kinds of recipes for all of the reaction templates we've got. For some of them, like Diels-Alder and stuff like that, Ene reactions, the templates are quite complex. For the simple ones, they're usually very simple things like this. So these are the recipe of what to do. And then associated with each of these templates that has the recipe is like a subroutine, a procedure for how to estimate the rate of that type of reaction. For the thermodynamic parameters of all the new species, it's estimated using Benson-style group additivity, where actually many of the group values were derived by previous quantum chemistry calculations. Actually, currently, most of them are from CBS QB3 calculations that my students did earlier. For cyclic and fused cyclic, especially fused cyclic compounds, the group additivity method doesn't work very well, and we have a lot of extra headaches. And fused cyclics are actually intrinsically three-dimensional, but we're trying to represent them as two-dimensional. And so fused cyclics are a nightmare, actually. This last year, a lot of my students in my group have been working really hard on trying to find better methods to calculate the thermodynamic properties of fused cyclics. And some of them in the audience, you can talk to them. And we define the rates. We pick a directionality of each type of reaction. We have rate estimation rules in that direction, and then we compute the reverse reactions using the thermochemistry. And you have to be unambiguous about which direction is forward and which one is reverse. And usually it's pretty clear, but actually certain types of reactions, it's kind of confusing about how to define which way is forward. All right. And then the tolerance, when to stop, is that we add up all of these fluxes, or we look at these fluxes across the boundary, and if any of these fluxes is greater than a tolerance times a characteristic rate, then we say we're not done yet, because we have some edge species that wants to be formed fast, and we have to put it in. But when all of the edge species all have rates which are negligible compared to the characteristic rates inside the system, then we say we're done. And you decide what's negligible by the tolerance you set, this epsilon. And this is how we define the characteristic rate. It's really the root mean square of all the rates of all the changes happening inside the system. So this actually, the characteristic rate can change a lot as the chemistry goes, and depending on the temperature. Like if the temperature is high and you're far from equilibrium, you'll have a really high characteristic rate because a lot of things are changing. And if you get close to equilibrium and the temperature is low, the rates can be really slow, and you have a low characteristic rate, which sort of changes the relative importance of adding something else. Can change it depending on what it's competing against, really. So you have the main reactions are running usually fast. You're adding some byproduct. You want to consider how much of your sort of the net change that's happening in the system is actually going towards this byproduct. If that number is big, then the byproduct's important. If it's a very small fraction, then you say, who cares? This is the algorithm. Probably too hard to read there, but you have it in your notes. And it's just basically what I showed you. Let's just do an example. So this is if you start with a mixture of methane, oxygen, and CO2, 1800 Kelvin, 1 atmosphere, isothermal, isobaric. We have a core of the reactions that are in the model. We have an edge. We started with methane, oxygen, and CO2. And we find that these are all the primary first-generation products you can make. We assess the rates of them. Methyl turns out to be formed the fastest. So methyl gets into the model. Then we regenerate. We recompute the rates, including methyl in our model. We've added all the reactions of methyl. And add additional species, like methyl can recombine to make ethane. Then the whole thing keeps going and going, sequentially adding more and more and more different species at each stage. And eventually, when it stops and it says I've reached the tolerance, in this case, it would have 112 species and almost 2,000 reactions. As you can see, this is a lot faster than trying to write down 1,200 reactions yourself, because the computer just keeps doing it. It just grinds away and it just puts them on. So that's a very convenient aspect of this, but it's really no different than what a human might do. So if you have a model that somebody else made for methane, they would one by one write them down. They'd say, oh, what's important now? Okay, let's put this one in. So it's a very similar thing. It's just we've automated it. Yeah?
So do you do one species at a time, or do you cluster species at certain rates and then just do it?
So the current algorithm and most of the papers we've published have just added one species at a time. We're having a lot of discussions inside the group that it might be better to add multiple species at a time. There's a lot of trade-offs. Yet you don't want to miss anything. And the one species at a time thing has a potential actually to miss some things. But you also don't want to add in extra species, because as you can see, these models are getting quite gigantic anyway. And if you accidentally add an extra species, it can get really out of hand. So there's a lot of heuristics about when is it good to add one species or multiple species. And you really have to do some careful analysis to figure out that. And I'd say that we haven't done that analysis as well. We've done a very careful analysis for the one species at a time case, and we understand that one really well. But the other alternatives, there's quite a few varieties of how you could do it, and we haven't really decided what's the smart thing to do. And an important thing to keep in mind with this algorithm is that the species you include in the model is only a very, very, very small subset of all the species you consider. That, just like how parents can have a lot of children, the reactions are like that. That if you have a small set of reactions, they can have a lot of child products. And so almost always the species in the edge is many more. So here we have 100 species in the core and like 1,800 species on the edge. And this is very typical that the edge is at least an order of magnitude bigger than the core. So that means from the point of view of computation, most of the computational effort is actually worrying about the edge species. We're keeping track of all these species, creating all these species, creating all the reactions that lead to those species, and estimating all those numbers. And most of those things in the end are never, ever going to make it into the core. So in some sense, we're wasting our effort computing a lot of properties of very minor byproducts which are never going to matter. However, if you don't compute them, then you're counting on your judgment about which ones are safe to not compute. Which ones can you just safely dispose of right immediately? And that's sort of the human judgment way of doing it. So the human judgment guys, they'll just think in their head, that reaction is never going to matter. I'm not going to write it in my model, because if I wrote it in my model, I'll get a new product. I'll have to calculate the thermo for that product. To get the thermo file, I'll have to calculate this rate constant. But I think it's going to be small, so forget it. So that's the human judgment way to go, is you're judging what's negligible, sort of usually pre-calculation. And this is, we're trying to do it post-calculation, which is safer, but has a computational cost. We have to compute all these numbers and keep track of all these species. So it gets to be actually, from the point of view of algorithmically handling it, this is the issue, is you end up with a lot of extra species and reactions. In this particular case, I think running on a singular processor, this model was constructed, it took 40 minutes of like wall clock time, I think, to do. So that gives you an idea of sort of how long it takes to build models. Major complication is chemical activation. I don't know, any of you taking Dr. Klippenstein's class? Has he got up to this yet? Chemical activation? OK. So this is a major topic that he's like the world's expert on. Let me just try to explain the issue. So if I have reactants A and B react, they can form C. If the pressure is very low, C will be formed out of equilibrium. I mean, actually, C is always formed out of equilibrium, because the C is formed by species that have enough energy to get over this barrier. So you're always like, you're like a skier, right? The system is like a skier, and it gets up to the saddle point, and it always comes in over the saddle point, and it's always way above the valley at the beginning. So the energy has a lot of potential energy at the beginning. So the species, when it's first formed, had a lot of potential energy here, and that's turned into kinetic energy of the vibration, things vibrating like crazy. And then there's collisions that cool it down. In cases where there's a second barrier from C, say, to D plus E, and this one is lower than this one, then a lot of these guys might go on and just immediately react, because they're way above this barrier, so they can just react before they have collisions to get trapped down into the bottom of the well. And this makes a weird thing, is that experimentally you put A plus B and you see D plus E come out, and you might not even see C at all if you're at low pressure. And so it looks like A plus B directly reacted to D plus E, but if you look at my reaction templates in RMG, there is no reaction template that would go directly from A plus B to D plus E in a single step. So somehow, I mean, empirically that's what's happening, but I don't know about it. And in fact, there is no single saddle point that connects these guys directly. I have to go over two saddle points, one here and then one here, to get there. So we taught RMG how to recognize when this can happen. When it goes A plus B goes to C, it considers the possibility that C could stay excited and immediately react to go to D plus E. And that way RMG will pick up all these chemically activated reactions. It's called chemically activated because this chemical reaction activates the C. It gives it extra energy. It's sort of a way of providing a whole lot of energy to C. And so RMG does this, and then it has to compute. You get a very odd P-dependent rate coefficient. This is one where, as the pressure increases, this rate going A plus B goes to D plus E gets slower, because the stuff gets trapped in C instead of going to D plus E. So it has like inverse pressure dependence. Most of the time, you do rates, when you increase the pressure, they get faster. This is when it gets slower. And also, it actually has really wacko T dependence, too. It turns out when you solve it. So anyway, we taught RMG how to do this. So here's a quiz for you. Can you write down the steady state equation for the population of C, which is the vibrational excited product? And the reason why I want you to do steady state is because you probably would apply the pseudo-steady state approximation to the C star. It's like an intermediate that's barely there. All right, so try to write down what you think is the steady state equation. A way to think about it is you write d population of C dt equals, and then you're going to set that derivative equal to 0. Right? D population of C star dt equals something. And then eventually I'm going to say that this is approximately 0 in order to figure out the steady state concentration of C star. All right, has anybody got it? Anybody willing to make a guess? Yes.
So I have it as being Ka times A times B concentration.
Concentration rate.
Minus C star times the quantity of KD plus K2.
Okay, C star times what? Quantity.
I just added the terms, so KD plus K2.
All right, looks good. So, and actually there's one more term. So one more term. That you can lose C star because it can get knocked down into C.
Oh,
Yeah.
what's the rate constant?
So they're called omega. So, so it could have minus omega concentration of C star, and then actually plus the summation of a whole bunch of other omegas that are all about C with every other possible energy.
That's going.
These are going up, yeah. So there's an up arrow there too. All right, so this is the equation. It's this thing. And the unknown is how much C star you got, right? And it's really how much of each of these C's at each energy level you have. That's the unknown. And so this is linear in those unknowns. You see this equation is linear in the unknowns? So this, you can write it as some giant matrix times concentrations of all the C's of EI. How much there is C's at each different energy state, this energy state. You can write this thing, and it'll equal something, some vector. This is a vector of all these different guys. Yep.
Can you use Maxwellian distribution for C star and other
Use a which distribution?
Maxwellian distribution?
No, because the rates, each of these guys depends on E. And this one is actually C of E. It's like E special. And this depends on E. Depends on E. And these guys also have some dependence on the E. And because of that, each of them has like its own balance equation that's kind of really different than the rest. And so when you solve this, you won't get a regular Maxwellian distribution or Boltzmann distribution or anything. You'll get some totally wacko distribution. That has a lot to do with the chemistry, because it has to do with these chemical rates of how fast you're forming and dissociating stuff. Yeah?
Could you explain that last term? Is it the activation of C?
Yeah, that's the activation that a collision might knock. It can go both ways, actually. Let's draw a picture. So a collision, if I have here's my special one. I'm calling this C star. My energy that I care about. There could be some population in higher states, and the collision could knock it down into this state. And there could be population at lower states, and the collision could knock it up. And so both of these terms can actually contribute to increasing the population of this state. And then similarly, there could be collisions that knock this down to any state. And actually, even something could even knock it up to some other states. And so to do it correctly, you should include every possible collisional energy change, because you have a state in a certain energy. The collisions can add or subtract any amount of energy from them, depending on exactly what happens in the collision. And so you have to have expressions for all of them. Now, this matrix, when you write it down, you end up with I'm going to write. We did this already, I guess we can erase this. This matrix is going to look like this. Let's see. So let's do a slightly more complicated case. Suppose you have like this. Here's C. Here's like this. Here's A plus B. Make C. You can make W, something else. And what's this, D plus C? Okay, because this could also happen, right? That the intermediate could isomerize. So now I have the states of C, the states of W. Each of these guys can interact all different ways. They all can move up and down every which way. And then they all can fall apart this way and this way. And I'm feeding it in, say, this way. Something like that. So that's just the overall system. So I'm going to end up a block of states that are states of C. And this block is all about collisional energy transfer. So this is all collision inside C. And then I have a block that's all about W. It's all about collisional energy transfer inside W. So these, the off-diagonal elements here are numbers that are like the omegas that are being for the probability of an energy transition from this state of C to that state of C due to collisions. And so I have all kinds of numbers in here, and this would be pretty much a dense block because every state of C can undergo a collision and get knocked into any other state. And it'll have bigger numbers sort of towards the diagonal because collisions that exchange a small amount of energy are more likely than ones that change a lot of energy. Okay, so that's what this will look like. And then for the reactions, C going to W, they only happen, they conserve energy. So the C isomerizes. C has a certain amount of energy. When it isomerizes, it makes W with the same amount of energy. So this block here is just diagonal. These are the Ks for C of E going to W with the same energy. So there'll be, and there'll be ones for the W's going to the C's also. And then all the rest of this will be zeros. And then there'll be a couple extra ones that are for going to the bimolecular products A plus B and D plus C. So that's what this looks like. And then down the side here, this is the matrix. And down the side here is the population of C of each energy state. All down here, and then population of W of each energy state. All down here. And you have some kind of equation like this and some big vector over there. And this is like the driving functions from the source terms from the A and B reacting. All right, so this set of equations is called the master equations. And they tell how not just every species is changing, but every energy state of every species is changing. Is that all right? It's a lot of equations, kind of a mess, but it's linear. So that's a good advantage of it. And so you can do a lot of special tricks because it's linear. All right. Now this is an example of a real system my group's done recently. Is recombination of cyclopentadienyl radicals to make naphthalene. This is actually very important towards soot formation. So some fuels make a lot of C5H5 as an intermediate product, and the C5H5s can recombine to make the C10H10. No, C10H8, naphthalene, and some H atoms, but it's a complicated process. So when they first recombine, they make this dimer as the initial product, but the barrier here is very low compared to the energy coming in. So oftentimes, this thing immediately isomerizes and forms all these other guys. So you get lots of different isomers of the C5H5 dimer. And then if you have a little bit of extra energy, if you're up in the Boltzmann tail, you might be at a high enough energy to get over to this guy. So you come in here, you go through all these guys, and you come out here, and it's this guy plus an H atom is formed. And so that's a way to get from the C10H10 potential energy surface to the C10H9 potential energy surface. C10H9 is a radical, and all the isomerization reactions of radical are much lower barriers than the isomerization of normal stable molecules. So once you get over here, there's a whole ton of things it can do, and eventually it gets to one that makes naphthalene plus another H atom. And that's the way you can make naphthalene. And this is quite important for getting towards polycyclic aromatics that are eventually going to form soot. But you can see the complexity here, right? There's all these little barriers here, and I haven't even drawn it up here. There's a whole ton of things up there. And a critical question is like, does these guys get stabilized? Is the pressure high enough that you Boltzmann populate these wells? If the pressure's high, that's what will happen. You'll Boltzmann populate them. And you're like in a diesel engine, maybe the pressure's pretty high, or a jet engine, right? It might be 50, 60 atmospheres maybe. And so it's possible that these guys get trapped, and then they can do bimolecular reactions if they're stabilized molecules. And so, for example, they might react with another radical and make C10H9 a different way. So it could be the multiple pathways of how you could get to C10H9 with different amounts of energy and have different likelihoods of what happens. And so, but at low pressures, these might not be stable. So this comes together and mostly comes right back because there's not enough collisions to trap it. But some of these guys have higher energy come out and they go over to the C10H9 directly. And they lose an H atom, they can't really come back because the H atom is going to go away. So that's this kind of system we would like RMG to automatically handle, and it can. So RMG can do this. So RMG enumerates all the isomers that could be formed. What it does is it basically knows anytime you have a reaction that forms a single product, like A plus B goes to X or C goes to X, it's likely that X will be formed energized. And therefore, you have to go and consider what X might do. And so X might break apart or X might isomerize. And then you keep track of this whole thing. So it finds it makes X, it says, oh man, I might make X Boltzmann if I'm high enough pressure, but I might make X energized. If it's energized, it might do something funny. If it's done something funny, I better find out what it is. And so it'll look for the products of X, the children of X. And then it will put together the whole sequence. A plus B goes to X, goes to F plus G, all together, and compute the pressure-dependent rate coefficient like that by solving the master equations approximately. And then if it makes a Y, A plus B goes to X, goes to Y, then the Y might still be chemically activated and do some more stuff, like in the case I drew here. So here it comes in, it forms the first product. This guy goes on and forms this product. This guy's even more chemically activated because you're way up high energy, and so it's way above this, and so it might dissociate immediately. And so RMG has to continue the whole sequence until you get to bimolecular products where they can kind of cool off by translating away from each other. If you want details of how this algorithm works, the rmg.mit.edu has some of the documentation, and also this is a journal paper by Josh Allen about it. All right, if you want to run RMG, there's some very good documentation. You should definitely look it up. Here's the GitHub documentation about how to make an input file. Here's what the output files will be. They're basically the chem.imp, which is like a chemkin format input file. And then it has annotated version, easier to read as a human, has a species dictionary, which has, like, for each of the name of a species, it has a picture of it and an explanation, so it helps the humans to know what the model's really saying. And it has estimates of the transport properties. That's a tran.dat. And there's a whole lot of scripts to do practical things that you want to do when you have large models. I recommend you use these tools to help you keep track. If you have models that have hundreds and thousands of species, it's very confusing. So this is to help you do things. And you can find these tools all on this website. And if you have problems, it's definitely possible you have problems. This is not commercial, well-maintained software with a professional helpline ready to answer the phone anytime you call. You get what you pay for. It's free. But we do have documentation of issues, and you can actually, if you find new issues, you can post them, and we eventually get around to fixing them sometimes. And there's instructions how to install it if you want to run it on your own computer. Actually, I think nowadays you can even, I believe you can run it on our computer. I'm not sure how well that works. We're trying to make it work so you can run our computer without installing it. But definitely you can download it and install it on your own computer. Does it work? So we've done it. So here's the best case was actually done in collaboration with Professor Law and Professor Combustion. That the Department of Energy gave us a lot of money, and a lot of experimentalists got money to measure properties of butanol. And they measured everything they could measure: flame speeds, products you make when you pyrolyze it, ignition delays, very high pressure ignition delays of all the isomers of butanol. Did all these things, and RMG built a model for all the butanols. And the model included 372 species, 8,723 reactions. And then we just ran the RMG predictions against all these experimental data. And you can see the RMG predictions are the curves, and you can see they look a lot like the experimental data for all these different things. So the RMG predictions are pretty good. Now, we were slow, and many of these measurements are actually made before we got the model working. But this one's, the measurements were made after we had the model. These are the concentrations of different species in a flat flame as measured by Niels Hansen at the advanced light source using a synchrotron photoionization to do mass spectrometry to measure all the products. And you can see we predict, formaldehyde, methoxy, propyl radical. I mean, all kinds of species that are pretty difficult to measure. He could measure them, and RMG had predictions, and the predictions are like, yeah, pretty close. I mean, they're not perfect, right? There's some deviations, but it's like, I would say that this is showing you can make predictions, and you certainly wouldn't be embarrassed to make a design based on these predictions. It might not still be good enough for what you need, but certainly you're pretty close. So this can work if you're willing to go through the whole procedure, do all the quantum calculations, everything. If RMG doesn't hit a bug, if you do everything right, everything's fortuitous, you can work out really well. And then recently we moved on from the C4s. We did the C10 fuels. This is a JP10, and you can see we do the pyrolysis pretty well. Again, not perfect, but this chemistry is pretty complicated. This is quite a complicated molecule, JP10. Tricyclic is intrinsically three-dimensional. We're representing it as two-dimensional, like this has some problems. But anyway, we did the best we could do, and it's okay. We also did oxidation and combustion of JP10, another paper about that. And then just recently, we've been adding heteroatoms into RMG. So this is like the first test case of heteroatoms. This is ethylamine oxidizing. Ron Hansen's group did experiments where they measured NH2 as a product from this, and they also measured OH. And the solid line is Ron Hansen's measurements with laser spectroscopy for these guys in a shock tube. And the dotted lines are the model predictions from RMG. And it's not perfect, but from the point of view of a lot of managers, this is like close enough, right? I mean, they're not scientists; they don't really care about the fact there's a little deviation here or something's wrong. But anyway, it's close. So we can do it. And the cool thing about making a detailed model is not just you get to trace the matches of the experiment, because I mean, you did the experiment already, you know the answer. So I could just take a magic marker and draw it through the line if I wanted, right? If all you wanted was a line that matched your data, just draw a line through it. So what you want is to know about what's really going on. So in this case, we have the ethylamine, we have the model. The experiments don't tell you what's going on. They see NH2 and they see OH. They don't tell you anything about any of the other species. But the model tells you about all the other species, and it tells you which reactions have high fluxes at which times, and the whole sequence of complicated things that are happening, and why does it have this goofball shape? I mean, that shape is not too obvious about why it goes up and goes down and gets flat, or why is it a long delay? It goes up and then it gets flat, and then it goes up and then it goes, why, right? It's not obvious. But if you do flux analysis on the model, you can see, it's this reaction's happening first, and then this other reaction's happening then. You can see follow the whole chain of everything that's happening. And then it depends what you want to know. But if you have a full model, it's like you have all the information about everything, and you can actually do the analysis and figure it out. Recently, we've also added sulfur. This is the pyrolysis of ditertiary butyl sulfide, a butyl group, a sulfide, a butyl group. And the products from that, as measured experimentally in a literature paper and in the model RMG predictions, you can see that they're not perfect. Like here, experimentally, there's more of the C4H10 than there is of the thiol, but RMG gets them backwards from each other. So it's like not perfect. But it's not too terrible. And then they added cyclohexene to the mixture with the ditertiary butyl sulfide and cooked them both together. And RMG predicted all the products from that. And then you can see, okay, the things change around because of the presence of the cyclohexene. And RMG predicts why that is and shows you make different products. In this case, it's again pretty good, but it's not exactly right. But this is the kind of level of what you can get. Now you have to expect some errors, right? Because we think the rate coefficients we can calculate within a factor of 3. It's not calculated within a factor of 1%. It's a factor of 3. It's pretty far off. And so you wouldn't expect that you'd ever get perfect agreement. But on the other hand, to get this kind of level of agreement, you have to have a pretty good model already. And all, again, with no input from the experiment. So it's just making a prediction. Here you can figure out, in analyzing the model, figure out what happened. What happens is that the thiol can unimolecularly react, but actually it can also do some bimolecular reactions with radicals. And in the system with the cyclohexene, the radicals are more stable, they're less reactive, and so this goes this way. In the system without the cyclohexene, the radicals are pretty hot, and they attack the thiol, and they make different products. And so this explains the change in product distribution. All right, another quiz for you. And I guess this might be the last one before we switch over to Professor Liu. So if you want to add a new element to a simulation, or to RMG, we need to teach the computer any types of new reactions that only that element does, that your previous elements didn't do. And you also have to add all the new functional groups that involve that element with their thermochemical group values to get all the thermochemistry estimated. And also you have to know if the presence of having those elements affects the reactions that you already had. So for example, if you had a reaction that was a H abstraction by a carbon-centered radical, if that carbon-centered radical is attached to a sulfur atom, does that change the rate? And if so, how much does it change it? So you have to go through, and every time you add a new element, you have to add a whole lot of new stuff to your databases of the estimation rules. In particular, most of the functional groups that are used for thermochemistry are of the type for tetrahedral carbons. So you have a carbon in the center, you have 4 atoms bonded to it. Now, when we're doing hydrocarbons, it's not so bad. You can have one hydrogen, 2 hydrogens, 3 hydrogens, 4 hydrogens, or no hydrogens bonded to your carbon. That's it. There's 5 possibilities. Now consider if I have, say, 5 elements instead of just C and H. I have C and H and O and N and S. How many different functional groups are there of the form of carbon with some number of these elements on the side? So see if you can do a little calculation of how many different thermochemical groups I'm going to need to consider every possible arrangement of carbon, nitrogen, hydrogen, oxygen, sulfur. Maybe that's too hard to begin with. Maybe just try the simpler one. Suppose you just add oxygen. So carbon, hydrogen, oxygen. Okay, and I just want to know how many different ways are there to have a carbon surrounded by some combination of carbons, hydrogens, and oxygens? So this is like a combinatorics question. How many different ways are there? Anybody have an idea? Yeah, Mark? So carbon, hydrogen, oxygen, Mark says it's what? 3 to the 4th. So CHO, 3 to the 4th. And the rationale here is that each, what? Was it? Change your answer? No. Stick with it? Okay. So the idea is there's 4 slots next to my carbon atom, and each one of them could have any of 3 elements, carbon, hydrogen, or oxygen. So by that argument, there should be 3 to the 4th. I think this might double count some things, so this might be an overestimate, but ballpark it should be right. So something like 3 to the 4th. So now let's consider we have carbon, hydrogen, nitrogen, oxygen, and sulfur. We still have 4 slots, but each of them can have how many different elements? 1, 2, 3, 4, 5. So it should be something like 5 to the 4th. So 5 to the 4th is what? It's like 600 something, is that right? 25 squared? 625. So something like 625. And again, you might double count some things that are repetitive. So this might be a little bit overestimate. But you can see I need so just to fill out the table of the thermochemistry group values, every time you add an element, you're like drastically increasing the amount of data you need. Unfortunately, all the data that's available is for CH and O, basically. And there's none for like things that have 5 elements all together in the same molecule because hardly anybody's bothered with those molecules. So you have to go do quantum chemistry calculations for these things. So each time I add it, I have to do hundreds of additional quantum chemistry calculations just to get thermochemical estimates. And similarly for every reaction family, I have to do similar kind of stuff. So it gets to be quite a challenge to make the more flexible you make your reaction mechanism generator, the more chemistry has to know, and the chemistry grows sort of combinatorially in a kind of bad way as the molecules get bigger and as the number of elements in the molecules increases. All right, I think I will stop. And what we're going to do starting tomorrow, I guess, is I showed you how great everything is right now. And tomorrow we're going to look behind the curtain and find all the flaws and the problems. All right, because it's not all as great as it seems. There's got to be a catch, right? You know, if every prediction was as great as I showed you there today, then the whole field of chemistry would have collapsed, and everybody would just be buying RMG copies. And I'm not a millionaire yet. So anyway, all right. So thank you very much. So we'll take a break, and at 11:15, Professor Liu will start the mechanism reduction.